Hi, welcome to our video on our paper Unlimited Sampling Live Below the Quantization Noise. So my name is Thomas Feuillen, and with Bhavani Shankar we are from SND, the University of Luxembourg, and our co-author is Ayush Bhandari from Imperial College. What I'm going to do is to go through here the poster. So what we're tackling is the acquisition and processing of radar signals, and those signals are high dynamic range in the sense of, depending on the range at which they are seen or at the angle at which they are seen, their received power might vary dramatically. So in a setting where you have more than one target, because of their angle or because of their range, you might have targets with a really large dynamic range and other with a really small amplitude. So your acquisition needs to be able to tackle both effectively. Here we're considering for this paper Doppler radar. So the received signal is simply a sum of sine waves whose frequencies depends on the range and whose power depends, as I've said, on the RCS and on the range at which they are seen. When you want to acquire this signal, you need to use an ADC, so an analog to digital converter. Here we are considering a mid-rise quantizer, represented here. And this type of ADCs have two main parameters. So first, their dynamic range, so the range on which they are able to acquire. And the second parameter is their resolution, often characterized as well with the number of bits, so which is here. So when you want, for example, to acquire here a two-tone signal, so in our context it can be a slow-moving target of large amplitude and a quicker one of smaller amplitude. One thing that you can do is prioritize the biggest target, so trying to avoid saturation by here, for a constant number of bits, increasing the dynamic range to match the signal. But by doing so, you are lowering the resolution. So here, in our toy example here, you see that actually the resolution is decreased so much that the information regarding the second target has disappeared within the quantization noise. Another thing is trying to retain a high accuracy, a high resolution by lowering here the dynamic range, but then by doing so you have saturation. So you see that there's clearly a trade-off between the two, and there is no one single solution to solve it if you use those type of classic ADCs. This is why here what we're studying is unlimited sampling. So unlimited sampling is a new framework of nonlinear acquisition that relies on the structure of the signal and here nonlinear modulo acquisition. Essentially, the signal is folded around the dynamic of lambda. So in our context, this would generate the following signal here. So we have set lambda to be this dynamic, and then when the signal exceeds it, then it just folded back. And by doing this, we solve these two issues. So first, there is no more saturation. So we're not losing anything regarding the signal because when it exceeds, it's just folded back down. A second thing, because here we can set the resolution lambda to be fairly small, we are also increasing the resolution of the acquisition. The next question is, given this red signal, can you still recover the blue signal of interest? And here the answer is yes. So in his seminal work, Ayush Bhandari showed in this, for example, in this theorem, that if what you are considering is band-limited signals, so for example, in our context, those radar signals, then if you apply this type of modulo nonlinearity before the acquisition, the sampling rate that you require to have a perfect reconstruction is simply a multiple of the one given by Shannon. And this oversampling, actually, if you look here, doesn't involve the dynamic range lambda that you use for the modulo. Of course, different algorithms exist and have been studied to the reconstruction. Here, in this work, we consider the unlimited sampling algorithm. So here, what we wanted is to show that this framework of unlimited sampling can work in an end-to-end fashion with practical hardware. The way that the system works is we have the radar, the signal that it generates passes through some preconditioning filter, and then these signals are first here acquired using a classic ADC, so with a large dynamic range. And this ADC has only a resolution of 8 bits, but also the same signal passes through the prototype modulo ADC that will fold the signal on a smaller dynamic range, and then it will be acquired using the same ADC, but with the same number of bits, but on a smaller dynamic range. So to generate here this near-far problem, what we are using is two target simulator, one strong target and one weak one. We've generated the acquisition with one strong target and one smaller target and one weak target, where for each measurement we lowered the power, and so we looked at the effect of that on the reconstruction. So looking at the first one, so here this is the time domain, here the frequency domain. The gray signal is the classic acquisitions. Here in frequency, what we can see for the gray signal is first one dominant peak, which is a strong target, some here harmonics due to the target simulator, and then here the weaker target. Now the black points here are the modulo measurement. These signals are reconstructing using the unlimited sampling algorithm that gives you here the red curve. And then let's postpone looking at this for a moment and look here at the blue curve. What is it? It is a reconstruction using those modulo samples, not using the unlimited sampling algorithm, but using unwrap. Okay, because you see, because we are folding, this problem is really close to just an unwrapping phase problem. Unwrap is not able to yield successful reconstruction. And to have successful reconstruction, you will need to increase here the sampling rate by a lot, and also this sampling rate will depend on the dynamic range that you use to fold. Looking here now for the red signal, again, the two peaks are clearly distinguishable from the noise floor. Lowering and lowering again the power of the weaker target. Now what you see here for the gray curve, you see that now we're starting to see the noise floor and the fact that the power of the weaker target is really close to the noise floor. So close that now you cannot really distinguish it from the noise. Whereas the modulo acquisition, because the 8-bit were dedicated to a smaller dynamic range, the effective resolution in the end for the successful reconstruction gives you a higher resolution and thus a lower quantization noise. So here clearly you can still distinguish the peak, and also you see that the noise floor has been lowered by 10 dB. So this brings us to the end of this small video. So what we tackled was the acquisition of HDR radar signals. We've seen that there's a near-far problem that generates an issue between saturation and resolution. We've studied unlimited sampling as one way of solving it. We've shown that it is efficient and effective both in simulation and in hardware with some real experiment. Actually, we've shown that we can lower, without changing the resolution of the ADC, we can lower the quantization noise by 10 dB. And this paper is actually the first time that the unlimited sampling framework has been used in an end-to-end fashion using commercial sensor in a fully practical setting. So thanks a lot for your attention. If you want to know more, please pass by a poster, and also we will have a live demo of this testbed here in ICASP in Rhodes. Thank you.